Today we want to talk about area now a little bit. So let's move in that direction, and that'll be this will be our last content for the day. So recall with me from your prior math experience that the arc length is r theta. Is this something you remember? In fact, it's somewhat definitional. If theta is measured in radians, the definition of a radian, the definition of the radian measure of an angle is the arc length divided by the radius. Isn't that like the definition of the radian measure of an angle? The radian measure of an angle, like what an angle is the ratio between an arc length and the radius. That's like what we meant all the time by an angle, right? Ratio of the arc. Anyway, so if that is still firm in your mind, then it's very clear, and you remember probably that the arc length, if we call it S, is just r theta, right? You have an arc formed by a 2 radian measure angle in a circle of radius 3 miles. Well, then the arc length is 6 miles, right? Because you get, for each radian, you're cutting off exactly a distance of 1 radius. I'm going to get this ratio thing going on. I don't know. Hopefully you remember that. Well, that's a little bit of me saying something about arc length. For a small theta, we think of course, in calculus as that we're very, very small. We get something that's basically a line. And we can think of the arc length, the area of that triangle, or that sector, as being 1/2 base times height. Now, what is the base? Well, we just talked about it a little bit. So here's a picture of a triangle here. If we're inside of some curve, or say a circle even, then we have this we might call the radius coming out from the center out to where we are. So the radius forms for us the height. That'll be, or take the role of h. And the base is, why is it r d theta? If we're calling this little angle here, we're calling this d theta. I guess I don't have it labeled there. Some really small angle. Why is that r d theta? If you were listening a minute ago. Yeah. Yeah, it's just the arc length formula, right? It's just r times the angle, right? That's what we said the arc length was going to be. And then the area of this triangle, we might call dA or something. So a very small, super, super infinitely small triangle. And so we're getting a very small triangular sliver of area. And of course it's equal to 1/2 times r d theta. So this little sliver, imagine I've blown it up so that it doesn't look very much like a sliver, but imagine that this is an infinitely small sliver. Well, then its area is given by this formula. It's 1/2 r squared d theta. And if you really understand that, you're really feeling good about that theory, then guess what we do? We can slap an integral on it and add them up when we're inside a region that's given by some strange curve, right? So here we go. Say this is some polar curve. I don't know. I'm just trying to make some arbitrary sketch. What we do is say we want to add up the area inside this curve from a theta value called alpha to a theta value called beta. How do we calculate this area inside here? Well, this time, instead of using a Riemann sum with rectangles that we're adding up little triangular slivers, aren't we? We're cutting up like a pie. Yeah, good question. So, integrating this expression gives the area inside of a polar curve. So notice that it's not so simple. It's not as just one mistake someone might make is just be like, oh, just take the polar expression and integrate it. Well, no, not quite. I mean, we need to integrate actually this expression where r, keep in mind, r is still, like we've been studying over the last day, r is a function of theta. So we have like a whole function in here. And once again, almost, well, I shouldn't say, I mean, some of these you could do by hand, but a lot of times we'll be focusing here on the setup. Give me the correct, and I think you'll find that to be challenge with some of these, even correctly writing a setup for some of these. So, if you're in a moment of need and you don't have this box memorized, you could think through this again from just pre-calculus principles. So let's do what I think is a fairly simple first one here. In a minute, we'll also do area between two polar curves and pieces of polar curves and all that. But here we're just straight up asking, like, how much paint do we need for this whole cardioid? Which is what this is. This is what we were discussing earlier. Let's do cardioid. So, and like I said, I'm going to give you permission to use FNN here. So we're using 1/2 the integral from alpha to beta of r squared d theta. So r is this. We'll plug that in for r. You'll need it to be squared then. You'll have a d theta at the end. What are the limits of integration? We need a 1/2 out front, and then the limits of integration are not a huge mystery on this one. They're just 0 to 2 pi. So I don't have much to say about that. If you run this on your calculator, feel free to, if you're in polar mode still right now, and some of you may be from having played around with polar yesterday and been doing your homework or who knows what, as you pull variables from your calculator, it'll look like this. Of course, you can do all of this with x's and y's, and you'll get the same answer. There's nothing special about the letter choice from our alphabet. And when you do that, you should get 6 pi, which would confirm that that's true. But again, it maybe makes us suspicious that maybe there is a way to do that integral. I don't know that we discussed this. This is not an integral that we ask you or AP asks you to be able to do. But I would challenge those who are interested to do it. It just takes one small trig substitution from the previous life. You might need something called the power reducing formula for cosine. Okay, you know how to turn cosine squared into something that doesn't involve a squared trig function, then you're home free. So that's the only barrier that makes this a little bit hard. But you should see that somehow this must be able to be integrated back nicely because it comes out so nicely here. So check us on that. See that you get the same answer we did. Any other thoughts there? That was the baby first example. Hopefully you understand at least how the machinery works. So now let's start thinking about area between curves. It's certainly true that sometimes it's just what you would probably expect. It's just the area of the outside one minus the area of the inside one. That's sometimes the case. But I'll just say this. Sometimes it's like that, but sometimes it's more complicated. So we'll do a more complicated example in a minute. So I've got this picture coming up here too. So again, I don't want you to stress too much over how these pictures look. You'll either be given a calculator, or often if it's non-calculated, you'll be given the picture or something. So don't stress out too much about this discussion, even though I hope you kind of have an understanding of this. So find the area that lies inside. You got to process even what this means. Even with the picture, I have to think hard about the logic here. Inside the circle and outside the cardioid. So where are we talking about, of course? Yeah, like the kind of the Batman area here. Let's shade it here. It's this region here, isn't it? Inside the circle and outside the cardioid. So as we go here, I should maybe have zoomed in on this a little bit. It's a little hard to see that this is the case. But all along the way here, let's take an example of a theta value here. Say right here. How do you calculate this little sliver of a triangle? Well, you have two triangles, really, right? And maybe I'll draw this bigger too here in a minute. But let me. What's a good color? How about orange? Okay. You have like this triangular region from the outside, one, and we're going to be, it makes sense in this particular picture to be subtracting the area of this little sliver that kind of overlaps here, right? And then you get the desired region. I'm doing white, how about you get this shape equals the desired area, right, of that little sliver up there. Yeah? Is that fair? Do you like my equation? Okay, so minus gives, right? Now that's not just one, that's just a representative piece. All of them along the way you could do the same picture for, right? And by all along the way I mean from what to what? Yeah, 0 to pi. And maybe you know that from the picture, but if you don't, how could you find it? So you didn't have the picture. What would you do? Yeah, set them equal to each other and solve, and you'll get 0 to pi. Okay? So, in this one, we'll just run with this and say, okay, let's just say it's 0 to pi. I think it's clear from the picture, and you can just quickly check too. Plug in pi here, you'll get 2. Okay. Yeah.
Can you explain to me how it's clear from the picture? I'm not clear.
Oh, yeah, so you can see that all right, as we draw this representative slice, these slices, it's clear that that's like, I don't know, pi over 6 or something. That was my representative slice, right? So say I wanted to draw all the slices, not just one representative slice. Which ones would you like to consider for this area that we're looking at? I think you'd want to consider starting at 0. And certainly pi over 6 and pi over 2, we want all these slivers. But then as we get to pi, I think we're done, right? Like if you go past that, then you're going to be doing like this triangle minus this triangle. It stops making sense, and it stops even being the area we're talking about. So, yeah. So I think that's my thought there. Okay, so the area we're looking for is, I think we can finally say after all that, 1/2 times the integral from 0 to pi, we just said, of, and this is a little messy, but what will it be? What's the outside? Yeah, let's make sure we kind of understand what the outside is and here and what the inside is. Minus 2 sine theta squared d theta. So, and again, I'm just inviting you to use your calculator to FN in that. Go ahead and do it. You don't need to hit pause on that too. Are we feeling good about the way I drew that picture and this really highly technical color explanation, hopefully? Honestly, the pictures here it's all about the pictures. On this one, maybe you don't fully feel that yet, but as we do some other crazy ones, you'll start to sense that. You just gotta draw a picture. I'm a big fan of drawing some representative slices in your region, just to make sure you're on track, like we just did now. Anyone have it for us? Buying you some time here. Point 4.858. And you're confirming in the back. Thank you. All right. Great. Let's move along then. Like I said here, to find the area between polar curves, sometimes it's more complicated. And honestly, I don't have like a great way of telling you when one is the other. One is better and one is. So sometimes it's shared by 2 circles. This could be, why is this more complicated? It doesn't sound on the face of it more complicated. Let's take a look at the picture and see if we can figure out why this is more complicated. It's not very complicated to draw. Of course, we're talking about this region. Right? The football-shaped area shared by the 2 circles. Okay, fine. But now let's start actually doing what we did before, and that is drawing representative slices. So as we sweep from 0 here, let's start with 0 and start sweeping. We want to start picking up these triangles here. And notice what's different here. Even though there are 2 functions at play, how do we calculate the area of these little slices? Notice what is and what isn't involved. What is the only thing that matters here? This boundary, right? There's no subtraction happening at all here, is there? To get these slivers that I'm starting to draw right now, I'm just straight up integrating this circle along there, right? I'm not involving the other function at all. This circle just isn't part of the equation yet. Now, until right there. In which case, now what happens as I continue to try to sweep radially across this region? Now the boundary changes. And as we draw representative samples here, we start getting them from the boundary, a different boundary. And again, now this one matters. This boundary matters. And this boundary isn't in the picture, right? It's the only, so we're dividing that up. And then now we're back to the other one here. And we finish it off there. Okay, so now we need to figure out how to write this actually. I think we all have the picture on this. We all have the picture maybe now, but it looks like we need to add some stuff up here. Let's think about this first region. It looks like we're going to be needing to do the integral from 0 to something, 1/2. And we never maybe even stopped to say which function is which. Which function is this? The one that we're in green here working with. Yeah, that's the one. As we do the green one, we're pulling values from here, and as we do that orangish color, we're doing r equals 1, right? Okay, so let's keep that in mind as we write this out. So 0 to something, we'll have to figure out what that boundary point is. So that's something we need to figure out, and this could be a non-calculator setup or something. So we need to figure that out. So 2 sine theta though squared d theta. And then notice in this problem, there's no subtraction of anything, really. We just are catching this region, and then we're gonna catch this region from I don't know what yet. I will figure out the limits of integration in a minute. But from something to something, we'll be integrating, well, this is nice, 1 squared d theta. All right, this is working out nicely. Does anyone have that intersection? Even without a calculator, you should be able to figure it out. What is it? Not quite. When is 1/2 our value of sine? Yeah. Pi over 6. Also, 5 pi over 6, and just confirm that that does look right visually, right? Right there and there is where we get these. It looks like pi over 6 and 5 pi over 6. I can be convinced of that, I think. So, I don't know. Now, we still have a little bit of soul searching to do because of the symmetry of this picture. One could do from 0 to pi over 6 for this, and then from pi over 6 to 5 pi over 6 to catch all of this, and then do another one of these, add a third integral from 5 pi over 6 to pi, and then I think we'd be done and we'd have the correct answer. But because we're lazy mathematicians, does anyone have a more efficient way in? Okay, so this one you want to do from 0 to pi over 6, and then just multiply it by 2. And that catches both the green regions if we know the symmetry. If we're solid on that, we feel good about the fact that those are going to be the same. And then the next one will go from pi over 6 to, I guess, to 5 pi over 6. Or you could do pi over 2, stop there, and just double the whole thing, right? So you have some options here. We just said, I think just now, 3 ways to do this. As long as you're okay, feel free. I'm inviting you to take full advantage of the symmetry of a given situation. Okay. So, like I said, this is where the work lies. Certainly, now you can take this to the calculator and figure out what this is. But like writing this stuff down, and you could obviously clean this up before you put it in your calculator. Please, and go for it. You know, obviously, you can just kill the 2 and the 1/2 here, right? That's the first thing I'd probably do. I don't want to do that immediately for those who are still trying to process what we've just done. But yeah, you could just type those in and add them. Okay. Let's give people a second there. Okay. I'm glad to have at least shown, I mean, we'll try and squeeze one more example in the last 4 minutes, but I'm glad we've seen at least 2 cases here where we have 2 functions at play. one example on the previous slide we just did where we're doing some subtraction between the two curves. We're getting these slivers that we have to subtract two slivers. And then another one here where you see that that's not necessary, where we have to kind of do an integral and the boundaries aren't intersecting, right? The boundaries aren't, there's never a sliver that cuts through both of our regions. And we don't ever need two boundaries there. What do you, anyone run this yet? What did you get? Kelly's my go-to here. 5? That's the total after doubling, after all that. Maybe. Someone could check her on that. Amber, you're supposed to be the backup here. Yes, you got that too. Okay. Thank you, friends. All right, let's at least set this one up if we can. Here we got, let's find the area inside the four-petal rose curve and outside the circle. So just to, again, be clear, we need to interpret that rightly. We're talking about this region, and I think after our discussion and Shivani's insight on the last one, I think this is a very excellent candidate for avoiding redundancy and making use of symmetry, right? Clearly, this looks like fun, but I'm definitely finding only one of these and multiplying it by 4. Or maybe you could even use more symmetry here.
One of them multiplied by 8.
One of what?
Half.
Yeah, like you can find half of one of these and multiply by 8 if you like. All fair game. Whatever you want to do. As long as you're right. Okay. So here, which case is this? This is maybe just the practice here, but what do we have to worry about here? Which would you like to do? 4. We'll do the first thing you mentioned. 4 times the integrals we need here. So I don't know, do we need to break this up again? As we draw radially, if we're like, say we start integrating from here across this region, how do we find the little pieces that constitute this region? Is this one where, I guess the question is, which of the last 2 examples we did is this similar to? The first one, right? We need to do this now. Both boundaries, as we draw a ray out, both boundaries are intersected. So we do need to do this kind of triangle minus triangle thing. So all the way along, in fact, along here we have integral minus integral. But we need to find the limits of integration too still. But so we'll do 1/2 integral from, what is that outside function? That's the 4 cosine 2 theta. And the inside function is just 2. So we're doing 1/2 r squared d theta. And then if we're choosing to do the whole, take one of these things and multiply by 4, then what are the limits of integration? For that, you need to solve Did you just guess, or you actually did? Okay. Yeah, it does come out to be that you'll have to divide by 2 at the end here, so you get pi over 3. You could say plus or minus pi over 3, but then we're dividing by 2, so like Derek said, you get plus or minus pi over 6 would be a good way to say this, maybe, from negative to positive pi over 6. Now be careful. I'm going to write that, and we're going to call that good. But be careful. That's going to give you the answer. Yay, 4 times all that. But the one thing I caution you about is if you answer this question by saying, well, pi over 3, or down here, pi over 6 and 11 pi over 6, careful, right? Don't be integrating from pi over 6 to 11 pi over 6, you understand? You're welcome to integrate from negative pi over 6 to pi over 6, or from 11 pi over 6 to 13 pi over 6, if you like, but don't be integrating from here to here, right? Okay, whatever you do. 8 times the integral. That's what you're saying. Yeah. Right. Is that what you said? Right. Absolutely. All right. Homework.